A student here at Berkeley and has worked on several projects, including ZEXE A, which he'll now present on.
Hi everyone, thanks for the intro. Peter, I'm Pratyush, and I'm here to talk about ZEXE A, which is our work on constructing a system for decentralized private computation. And this is joint work with Sean at ZEXE, my advisor Alessandro, Matt and Ian, who are at GHU and now I think at Cornell Tech still, I'm not sure, and Howard. Okay, so let's get started. Okay, so today if you want to compute on distributed ledgers, like if you want to have a smart contract system, we have a number of these, right? We have Ethereum, Tezos, EOS, and more popping up by the day, right? And how these, there's like lots of differences between them, but the common thread amongst all of them is that they all work by re-execution, right? What this means is that whenever you propagate a transaction to the network, every node to verify or validate that transaction has to re-execute the computation inside that transaction, right? And if everybody agrees that this computation outputs 10, then the transaction is a valid transaction and it's confirmed on the ledger, right? Okay, this is the standard model nowadays. Now this sort of re-execution model has a couple of issues in terms of scalability and privacy. From the scalability perspective, the issue is that you have this piece of computation, but your network might consist of nodes which have differing computational power, right? You might have like a server class machine, but also a mobile phone in the same network. And if all of them want to participate in the network properly, they all have to validate this transaction, which means they all have to execute this computation, right? And this means that now your weakest node is sort of the bottleneck in the network, right? And this is independent of any consensus layer improvements you could think of. Even if you had this ideal consensus or consensus mechanism underneath, you would still have to validate each transaction, and so you would still face this weakest node bottleneck, right? Okay, so that's from the scalability perspective. From the privacy perspective, right, when you send out this transaction to the network, anyone can see, first of all, which program is being executed, right, which contract is being executed, what data is being provided as input to the computation, and finally, who invoked or who is like the caller of this program, right? And this information is permanently stored on the ledger for all time. And as methods of analysis get better over the years, this information only becomes less and less private, right? Any questions on this? This makes sense, hopefully. Okay. So what we do in ZEXE is construct a ledger-based system that allows users to conduct these computations offline and then just publish attestations to the correctness of these computations, right? And here ZEXE stands for zero knowledge execution. We'll see where these two parts come in a second, right? And the properties that we get in ZEXE are, first of all, privacy. This is where the zero knowledge part comes in. And the idea is that the transaction reveals absolutely no information about the offline computation. So what we saw on the previous slide, right, information about the executed program, the input data, the caller, all that information is supposed to be hidden in ZEXE, right? So every a transaction for every computation looks the same. They're all indistinguishable. Okay. So that's in privacy. In terms of efficiency of like solving the scalability issue, what we achieve in ZEXE is a property that every transaction can be validated in time that's independent of the size of the computation. And concretely, for our implemented system, we have the transactions are less than a kilobyte in size, no matter how large your computation is, and they all verify in less than 50 milliseconds. Yeah.
I don't understand what's the meaning of reveals no info about the offline computation. I need to know what you computed, no?
No, you don't. We'll get to see that. Yeah, that's a really cool property. Like, if you're not part of the group, or the person who is involved in the execution of the computation,
hiding some of the data that goes into the computation. Also.
All of the data. What you'll know is that this transaction, whatever computation occurred in the transaction, you'll know that it was correctly computed, but you won't learn any other information about that computation. Yeah, we'll see how we achieve this in a second. Yeah, it's a pretty non-intuitive or counterintuitive sort of property. Just take it on faith for a couple of slides. All right. Yeah, so for scalability, as I was saying, right, the transaction is the size of the transaction and the verification time is independent of the concrete computation that you're performing. Right? Even if you have this map-reduced size cluster making a computation, the transaction in the end will still have these properties. Okay. And finally, to achieve these properties, we don't sacrifice in terms of functionality or expressivity. What we have is that we can support arbitrary user-defined functions. So whatever computation you want, you can express it in this system. We isolate malicious functions from honest ones. So if you have some malicious attacker that's putting out like a bad computation, that computation won't affect the execution of honest computations. And also, we don't completely isolate. There's still like some sort of managed communication between these different computations. So functions can interact. Okay. This is all like nice properties, but also we don't just have a theoretical framework. We also show in the paper how to construct some example applications, such as private user-defined assets, so multiple tokens that are completely offer zero cache style privacy. Also, private stablecoins, which have different sort of properties around issuance and transaction validation and stuff. And also exchanges, decentralized non-custodial exchanges to trade these assets. Okay. And we'll dive into a couple of these in the talk. Okay. Any questions? Yeah, feel free to interrupt at any point to ask any questions.
Is anyone actually building any of those three things?
So I'm not. People have reached out. I don't know where it's gone. We have an implemented system, which we'll talk about at the end. The code is available online. I haven't yet published. I think doing this would be the easiest to get started off. I haven't yet published code for how to do that in our
Stablecoin one has really interesting legal implications, or doesn't it?
Yeah, it would. Yeah.
What is a stablecoin?
So stablecoin is basically the sort of. If you know about Bitcoin, the value fluctuates, by thousands of dollars over a week or so. The point of a stablecoin is that its value is sort of pegged to some, other currencies in some sense, like real world or cryptocurrencies. And the idea is that the value doesn't fluctuate as widely or rapidly.
What prevents it from fluctuating?
So the idea is that there's some collateral backing company which says I have $1 and I'll give you this token because I have $1 and now you can redeem it for $1 in the future. And the idea is the value doesn't fluctuate too much. Or it's a basket of currencies in some sense. For example, I think Libra is also, their value. I think they're a stable coin. Okay.
Sounds like from your puzzle that private coin and private stable coin are different problems. It's the stable.
Oh yeah, yes.
It's the same problem. The stable doesn't play any role here.
Well, no. It's just that every stablecoin that's been released thus far has been transferable on a completely public blockchain, like Ethereum or something like that. And this is partly why I think regulators are somewhat comfortable with the concept of stablecoins. I think it'd be very interesting if there was a stablecoin that traveled over a more private blockchain.
The key idea is basically that some stablecoins are somewhat more regulation friendly, right? And I guess going from here to here, the additional part is adding this sort of regulation friendly nature while still maintaining some sort of privacy.
Sounds like you said that stable is harder than normal coin.
Just regulated.
Because of the regulator.
The regulation.
You are wondering about private and regulator, the interaction between private and regulator.
Yes.
How do you satisfy regulations while still having...
Okay, now I understand.
Yeah.
Maybe you should change that to regulation friendly or something. Okay, all right. So in this talk, I won't talk about ZEXE A, the full general system. Instead, we'll see how you can take these ideas that I talked about to construct a couple of the applications, namely private user-defined assets and DEXs, and maybe if you have time, I'll dive into these private regulation-friendly coins. Okay. All right. So why digital assets, right? So if you look at smart contract systems today, probably the most successful and widespread application of these systems is to issue custom user-defined tokens or assets, right? So if we're able to support this use case, you're already supporting if ZEXE can support this use case, it's already has a useful application right there, right? And also the idea is that if you look at systems like Ethereum, you have these ERC20 tokens, you have 721 tokens, you have these regulation-friendly stablecoins, and all of these have like sort of different issuance properties and transaction properties and controlling authorities. So if you're able to support this sort of wide variety of use cases, then it exercises the flexibility or functionality that I talked about on the previous slide. Right. Okay. So once you have these, like the natural question that comes up is how do you actually go around trading these, right? Because people want to trade assets, right? So today, there's two primary methods of doing this, right? You have these centralized exchanges, and the idea is that I, as a user, give up control of the asset to this third party called the exchange, right? And it manages trades on my behalf because it has full control over my funds, right? The problem with this is that it can lead to, and has led to in many cases, loss of funds due to fraud on the part of the exchange, security breaches, or just plain old human error. Like millions, probably maybe billions by now, of dollars of like user funds have been lost because of mismanagement at the exchange. Okay. But okay, it's not all negative. They do have some nice properties. First of all, they are more efficient in the sense that because now every trade is just like changing some entries in the database of the exchange, you don't have to go to the blockchain for every trade, for every transaction, right? And this results in infrequent on-chain activity, which is a plus, right? You don't want to wait like 10 minutes or an hour for your trade to go through. Okay. And they also have some notion of privacy, right? Because as I said, you're only updating entries within the database of the exchange, right? Only the exchange really learns information about the trade, like who's trading with whom, because none of it really hits the chain until it's in a mass accumulated package. None of that information really goes to the blockchain about individual trades. Okay, only the exchange sees this information.
And the US government.
And the US government, sure, through the exchange. Yes, okay. So going back to this point, so to solve this problem of custody of assets, and in some sense, okay, not yet. Yeah, just mainly to solve this probably a problem of giving up the custody of assets to this third party, people have come up with decentralized or non-custodial exchanges. And the idea with this is that users retain custody of their assets throughout the trading process. At no point does the secret key for a particular account or whatever go to a third-party exchange. The user has full control at every point in time. Okay. And in some sense, they're responsible for performing the trade. But this brings its downsides, right? For almost every non-custodial exchange that I'm aware of, you have to perform an on-chain transaction for every trade that you make, right? So now you incur the latency of the main blockchain. Okay. So you lose out in terms of efficiency. But also, existing blockchains are all, public. Ethereum, you can see what transactions are occurring at any point in time, right? So you lose this privacy, somewhat privacy guarantee that you had from the centralized case, because now the observer can see, any observer can look at the blockchain and see, this trade for asset A, asset B at this price occurred, right? So you don't have any privacy. Yeah.
So there are also exchanges like Plasma, then you don't have this on-chain activity in Plasma, right?
It's like you have like sort of this aggregator, right, which comes in and rolls up. So you would have privacy with respect to the...
I'm not talking about privacy, I'm talking about on-chain activity.
Yeah, so there it's all aggregated, and in some sense only the aggregated transaction goes to the ledger. Yeah. Okay. So in this talk, because there are solutions for this sort of scalability issue, right, including Stark DEX and Plasma and such, I'm going to focus mostly on the privacy aspect, this privacy shortcoming, right? And concretely, so let's take a look at what the concrete leakage is, right? The first problem is that, as I said, every trade goes on the ledger, right? And this reveals information about who's performing the trade, like who the sender and receiver are, what assets are involved, and what the exchange rate for these assets was, and what the amounts traded were, right? And this has a 2x effect. First of all, it negatively impacts the financial privacy of individual users, right? Because it is all publicly viewable on the ledger. And this, first of all, reduces fungibility because you can see the history of all the funds in a trade. And it can also reveal secrets about the proprietary trading patterns of a particular user or something, which they might want to keep secret, right? So at first, it harms user financial privacy, but maybe you're like, okay, this is acceptable. We are gaining this decentralized. We don't have to lose custody of our assets. Maybe it's okay, right? But so it's not just individual users. This sort of lack of privacy also impacts the global security of the entire, not only DEX, but also the entire blockchain, actually. For example, one problem is with front running, right? So if you're a miner in Ethereum or something, you can see big orders as they go out. And then you have some information about how prices are going to change, so you can place your own order before the transaction is confirmed. And now you can benefit or profit off of this difference in prices. Right? And this is not just a theoretical attack. There's been a series of works by folks at IC3 over at Cornell Tech, like the Flash Boys 2.0 paper, where they show how you could actually leverage this sort of information to actually make profit on the network. And they have other attacks where this sort of public information allows you can even destabilize the security of the entire Ethereum blockchain, for example. They have some cool attacks there. Yeah, so the point is that this is not just a theoretical attack. It actually happens or is possible to execute in practice. All right. So let's see how you would solve this, right? So first, we would construct these first private user-defined assets. And then we would see how to construct this private DEX to trade these assets. All right. So let's get started. Okay. So our starting point will be the zero cash protocol. And we'll focus on this, first of all, because it offers, for a single asset, the best possible anonymity guarantees that you could hope for. And also, it'll be like the building block for our actual construction, as you'll see. Right. So in zero cash, what happens is that each transaction consumes some old coins and produces new ones. And the idea is that the sender, receiver, and value are all provably hidden. Each transaction looks indistinguishable from any other. Okay. In a little bit more detail, each transaction contains, for the old coins, it produces serial numbers for the spent coins, and contains, for the new coins, commitments to serial numbers for those new coins, right? So as you append more transactions, the idea is that even if I spend that coin produced in the first transaction in this new transaction, in this latest transaction, nobody will be able to link that commitment to this serial number. So, okay, and the idea because the commitment is hiding in some sense, right? Along with the guarantee that there'll be like a zero knowledge proof somewhere in here, which guarantees that you're not making money out of thin air, that value is conserved across transactions. Okay. All right. And the anonymity guarantee that you get is basically that when you spend a coin, the anonymity set is a set of all possible or all past coins that were created, right? So when I have SN5, it could have come from any one of the commitments in the past. There's no way to figure out which commitment it came from or which coin it came from. Okay. Any questions about the anonymity guarantees here? No. All right. So let's dive in a bit more detail. So yeah, this is the transaction, right? As I said, it has serial numbers and commitments. And what it additionally contains is a zero knowledge proof, which proves some information about these two things. Right? So first, the proof talks about the old coins that are consumed in the transaction. And what it shows is that these old coins that I'm spending exist. They're actually produced in some past transaction. And this technically is done via some proof of membership in a Merkle tree. But the point of this step is that I'm not making money out of thin air, right? So that's I'm spending money that I created. The next point is I want to show that the serial numbers of the coins that I am spending, these serial numbers were derived correctly from this old coin, right? I'm not making up incorrect serial numbers. And this is done again technically via some sort of PRF derivation using this information, not super relevant for the talk. So what I know now is that the coins that I'm spending were created in the past and are not being double spent because the serial number is derived correctly and it's supposed to be unique. All right? Okay. And finally, about the new coins, we just want to show that these commitments are constructed correctly. They actually correspond to some, public key address or something and actual value. And finally, we want to prove that that value is actually conserved in the transaction. That the sum of the old values is equal to sum of the new values, and maybe some change information for transaction fee. These are the properties that you want in a private transaction, right? And the idea is that the zero knowledge proof enforces these properties, but courtesy of the zero knowledge property, it reveals no information about any of the old coins or the new coins or anything else. All you see is that the transaction has some serial numbers and some commitments and a zero knowledge proof. Okay. Any questions about this? Yes, it gets only more technical. This is like the key building blocks. If you have any questions, maybe ask them now.
Good tech.
Okay, let's dive in then. All right, okay. So Zero Cash, as you saw, achieves this ideal anonymity guarantee for a single asset on a single blockchain. It's been deployed as Zcash already, right? So the question that we want to ask is, how do you achieve this, this ideal privacy guarantee for multiple user-defined assets on the same blockchain, right? That's what we want to answer. Now, a straightforward or like naive way to do this would be to, if you have asset A, asset B, asset C, just independently run instances of the Zero Cash protocol for asset A, asset B, asset C, right? So you have Zero Cash A for trading in A, Zero Cash B for trading in B, and Zero Cash C for trading in C, right? Can anybody tell me like what the downsides of this approach are? Yeah, so A, you can't move between them, right? So that trading application that we had, the DEX, it doesn't work, at least not straightforwardly. What's the other downside in terms of privacy?
You can tell which asset somebody's.
Yeah, exactly, right? So now your anonymity set is partitioned by the assets. If so, Zero Cash A will have its own anonymity set, Zero Cash B will have its own anonymity set, and so on for C as well, right? And ideally what you want instead is that A, B, C, they all share the same anonymity pool, so you don't learn which asset is being traded. Right? Okay, so let's see how you could do that. So we'll take the construction on that previous slide and modify the structure of our coins a little bit. All this information is the same. You don't have to worry about that. Okay, so instead of now just storing values inside the coin, we'll also store an asset identifier, right? So now each coin has the asset ID and the value. And what the proof will ensure now is that for every asset ID, so for every asset in the transaction, the value of that asset is conserved. Right? So if you have asset A and asset B in the same transaction, like C1 old is asset A, C2 old is asset B or something, what you'll ensure is that asset A's value is conserved in the transaction and asset B's value is also conserved independently. Right? There's a little bit of a technical note on how to actually introduce value and create this asset ID, but we won't go into that. You can look at the paper for details. Okay. So the point is that now this transaction reveals no information about the asset identifier or the value, right? Because again, the zero knowledge proof hides all this information, and the rest of the information is just some serial numbers and some commitments in the transaction, right? So is it clear why you don't learn any information about these things? About the ID and the value, right? Okay. See a couple of use cases. Any questions? This is very straightforward. If you hide the value, you just replace the value now with the ID and value pair. Okay. Right. So this, achieves our goal of multiple private user-defined assets in the same transaction with the same anonymity pool, but it doesn't achieve, our ability to trade between assets, right? So your question about how to trade between them, assets are still isolated. There's no sort of way to go from asset A to asset B in some sense. Okay, so the question is how to enable applications that interact with multiple assets at the same time, like the DEX application. Okay, so what we'll do now to get that is we have the same stuff as before, but now inside the coin, what we additionally store is we have the ID and the value, but also some auxiliary information, which we'll use for application-specific purposes, and death predicate. You can think of this as like a sort of Bitcoin script kind of thing, right? And the idea is that when I spend the old coin, not only should the value of the assets be conserved, but also the predicate or the Bitcoin script of the old or the spent coins should be satisfied. Right? You could just think of this as analogous to a private Bitcoin script in some sense. Right? And the idea again is that if you construct a zero knowledge proof correctly, you can ensure that this transaction, again, it reveals no information about the ID value or the predicate of the consumed coins, right? Now, this is a bit of a tricky step. I won't quite describe how we achieve this in the paper. Yeah, but you can do this. Okay, any questions about this? So the difference from the previous slide here is basically that instead of just ensuring value conservation, now you also plug in some arbitrary computation inside your coin. And the idea is that if you want to spend the coin, then that predicate or that script has to be satisfied. And the input to that script is the entire transaction, basically. Yeah.
I was just curious about this no information thing there. I wonder, are there cases, is this kind of like an information theoretic, no information? I just wondered what happens if in certain small pools of people using an asset, or with lots of transactions, or maybe something a little bit different, more complex than these assets. Is there some information theoretic guarantees, or they're not?
So it does depend from application to applications. If you're an application, essentially the guarantee that we provide is if you're part of the, it's a bit complicated, I guess. But roughly the idea is that, for example, for simple asset transactions, then your guarantee is the entire anonymity set, right? This information theoretically guaranteed. The zero knowledge proof has this property called perfect zero knowledge, which means that no information is revealed about any of this stuff. Concretely, if you have a specific application which requires you to reveal information to another party, then that information is revealed, right? But that's artifact of the application and not in some sense of the system, right? You could, if you redesign that application to not reveal information, then there would be no leakage at all from here. Maybe you can see in a second how it would work when we get to the DEX example.
That's good enough.
Okay. All right. So any questions about this part? Any other questions? No? Okay. All right. So let's see how we can use this, this notion of death predicates or private Bitcoin script in an actual application, right? What I want to emphasize just a second is that these things, these predicates, can be any arbitrary computation. Just not, I'm talking about Bitcoin script, but Bitcoin script is just an analogy. You can put any arbitrary computation you want in here. Yeah.
You compare them to Bitcoin script and call them something predicates?
Death predicates in some sense, because these coins are dying.
Yeah, okay, yeah. That's good. Okay.
Because in the paper we'll also have birth predicates. I don't know if I have time to get into that. How much time do I have?
I'm supposed to know that.
Okay, I have 20 minutes. All right, okay. Yeah, so any arbitrary computation can occur within these scripts. Okay, so let's see how we can use these for a concrete application. And we'll take a look at these private atomic swaps. And why atomic swaps? Because there's, in some sense, the key primitive for constructing DEXs, right? When you're trading with somebody, you don't want it to be the case that they get your funds, but you're left with nothing, right? You only want the trade to go through if both of you get what you wanted out of the trade. Okay. So what we'll do is, so let's say I want to trade my asset for somebody else's asset. What I'll do is I'll create this coin which has that asset ID 1 and the requisite value and some auxiliary information. We'll see what's in there. And I'll set the death predicate for this coin to be this exchange death predicate. So let's take a look at what it is in there. So let's imagine this coin is a part of a transaction with some other input coin and a couple of other output coins. Right. What the exchange death predicate will enforce is that it'll take a look at all the coins and it'll say, okay, look inside C1 old, specifically the auxiliary information, and find out the ID and value of the coin that you want in exchange, right? So, so let's say C1 is of asset type A, and I want to trade for asset B. I'll put the ID of asset B in here and the value that I want in exchange as V star. Okay. The exchange death predicate will check that the other input coin, so this one, actually has that relation. It is of ID star and has the correct value. And then it will perform the swap. It will make sure that the output coins have the correctly swapped values and IDs, and it will make sure that they're addressed to the right people, right? So the new coin is going to my address that I specified in here, and the other new coin is going to the other party in the exchange. Okay. Does it make sense? Right. So the idea is that this predicate will only be satisfied if the other coin in the transaction or the other coins satisfy this set of conditions, right? Yeah.
What if there are multiple possibilities that would still satisfy the predicates? So if there was a spread in a simple atomic swap where someone's willing to sell for at least 10.
Yeah, you could change this value condition to be like within plus or minus 10% or something. You can set it to be like whatever you want.
So yeah, so that's, I mean, in a sense, that's the hard part. Is that the predicates can only might loosely constrain the potential outputs. How does the system end up resolving between if there's several ways of killing the old coins that would satisfy their death predicates?
So that depends, in some sense, how you deploy this exchange death predicate in a concrete application. We'll see in a bit how you would do this in an actual DEX, how you would use this to construct some sort of DEX. Okay. Any other questions about this? Okay. All right. So for the DEX, we have like one component run, and we have a private atomic swap. But we have a couple of things that we didn't talk about. First of all, we didn't talk about how to construct or create orders, right? How to discover other orders in the system, and finally, how to once you have agreed on some sort of asset value pair, how to actually go ahead and finalize the trade. Okay. So let's take a look at how to do this for one popular sort of exchange DEX architecture. Right. So in index-based DEX, right, you have this sort of public data structure called the index, which maintains a list of intentions to trade. Right. And what I mean by intention is just it contains the asset pairs, nothing about the actual value of the asset. Right. So if I am somebody who wants to trade, I can go ahead and publish, I want to trade asset A for asset B. Please contact me at this public key, encryption public key or something. Okay. The idea is that people who bring the liquidity to the trade, the makers, they're the ones who go and publish this on the exchange. Okay. On the index, sorry. All right. And the idea then is that once this intention is published, a taker can go ahead and scan this index and interact with the makers to fill out the orders that they see. Right? So if they like an order, I can go ahead and fulfill that order by interacting with the maker. Right? And an example of this is the swap protocol. So it's actually deployed in the real world, not something I'm making up. Okay. So let's see in a bit more detail how these things work. Right? There's actually other kinds of exchanges as well, which we talk about in the paper. There's different sort of like ZEXE exchanges. You can take a look at the paper if you want to see how you would get privacy for those as well. Okay. All right. So back to our index-based DEX, right? So this is the index. You can see it has, somebody published, I want to trade some asset for some other asset, and their encryption public key, right? And so let's say this maker comes along and publishes, says, I want to sell A and buy B. Please contact me at this encryption public key if you want to trade with me. The taker says, okay, this looks, I want to, I have some B and I want to get A in turn. And the idea is that now they can interact via this public key, this encryption public key, agree on the terms of the trade, right? And in the end, the taker will get some sort of transaction that they can publish to the ledger, at which point it'll be finalized. Right? Okay. Any question about the model? Should be straightforward, right? Let's take a look at what the privacy leakage of this is, right? So this transaction which goes to the ledger, it reveals a few things, right? First of all, it reveals the addresses of the maker and the taker, right? It also reveals the values and which assets are actually being traded, right? And this, so you learn the identities and assets and values. And this leads to a couple of different kinds of leakage, right? First, it leads to this sort of trader anonymity. So if you want to prevent this, you end up with two sorts of properties. The first is trade anonymity, which hides, in some sense, the transaction graph, and namely the addresses of the maker and the taker. And trade confidentiality, which hides information about the assets and values used in the trade. Now, these two properties are useful to formalize because they prevent the problems that we saw earlier in the slides, right? Right? So trade anonymity preserves the financial privacy of the users by hiding the transaction graph. And trade confidentiality, it prevents front running, because if you don't have this, right, miners can see what the asset pair is, right, and what the value is, and they can do that front running that we talked about earlier. With trade confidentiality, they have no idea like which asset pair is being traded, and so they can't front run. Okay. Does it make sense? Like why these two properties are actually useful for you? Okay. So let's see how we can achieve these properties, right? And construct this private index-based DEX. Okay. So your maker, as before, comes along, publishes their entry into the index. The taker says, "Okay, I like this. Let's interact," and they agree on some price for the trade, right? And now this is where we differ from the original protocol, right? So the maker, they construct their coin as before, right, with asset A, value VA. And now inside the auxiliary information, they'll put, I want to get a coin of asset B and value VB in exchange, right? And they'll set up the debt predicate to be the exchange debt predicate that we saw earlier, right? What they'll do is now the maker sends over this coin along with the secret key that's needed to spend the coin, right? The corresponding secret key to this public key. It sends that coin to the taker, and let's say the taker actually has, a coin C2 that satisfies the conditions of the trade. The taker can then go ahead and publish and construct a transaction that satisfies this exchange as predicate. And and the point is then they can publish this transaction to the ledger. And because this transaction has the privacy properties we talked about earlier, we get trade anonymity because it hides all information about the sender and receiver, right? In this case, the maker and taker. And it also hides information about the asset and value and values involved, right? So you get trade confidentiality. So you prevent, leakage for the privacy of the users, and you also prevent front running like attacks. Okay. Any questions about this? No. Okay. Just trying. All right, so we constructed these private user-defined assets, and we saw how to use this custom access, these debt predicates to get private DEXs, right? I'm not sure. How much time do I have? Like 10 minutes or so? Okay, maybe I can cover stable coins as well. So we had those, we've got our private assets and private DEXs, right? But now let's say you want to construct an asset which has some sort of different transaction policy, right? For example, if you have a normal ERC20 token, that corresponds to this sort of value conservation property, right? But if you have a stable coin, then you might need to implement some policies which correspond to regulations, right? You might want to, for example, implement blacklisting. I can't, this transaction did not involve any of these blacklisted addresses, or this transaction is only going to one of these whitelisted addresses, or maybe this transaction pays taxes or something like that, right? All kinds of regulations, you might want to implement them, and while still having privacy, right, against everybody, including the regulatory authority. Okay, so let's see how you can achieve this, right? So what we do is now this is all same as before. What we'll introduce is we'll have the debt predicates as before. What we'll also introduce is birth predicates for the new coins. And the idea is that along with the value conservation policy, what we'll require is that the birth predicates for the new coins is satisfied, right? So for every new coin that's produced in the transaction, the corresponding birth predicate is satisfied. And we still have the debt predicates of the old coins still being satisfied. And the idea now is that, for example, you could use this birth predicate to ensure that this new coin was not produced in a transaction which had these blacklisted addresses, right? The point is, so now when I want to use this new coin in a future transaction, right, what anybody who's using that coin will know is that this corresponding birth predicate was satisfied, right, inside the coin. And so they'll know that the coin was created in good conditions, or like regulated conditions. Right, does that make sense? At a high level? Yeah. So this could be implementing a blacklist, right? The birth predicate says, C1 old is not a blacklisted coin, C2 old is not a blacklisted coin, right? And when I use C2 new in a future transaction, I'll know that blacklist birth predicate was satisfied when the coin was created. So then I'll know that this coin is regulation friendly, right? Yeah.
I'm curious how complex can these birth predicates be? I mean, is there?
It depends entirely on you. So you could set it up to be this massive computation. You could set it up to be like just checking 2 or 3 small conditions, anything. Yeah, you could set it to whatever computation you want. I mean, you have to probably fiddle around with how to do that efficiently in some sense, and like without revealing too much information. But depending on your application, you can set it up to do any arbitrary computation inside this. And the point is that the transaction would still be verifiable in time independent of that computation. Yeah.
What was the inspiration for this work, other than the fact that once you have death predicates, it makes sense to have birth predicates? Was it actually that you've looked at other stable coins and seen that they implement blacklists, or was it that you hypothesized that they will implement blacklists one day?
So the applications actually came as like post facto once you had the system in place already.
Right. What you felt like you could do with birth predicates?
The birth predicates are actually, in some sense, okay. So as we'll see, like ZEXE itself does not have a concept of a coin or any value or anything underneath. And so what you actually need these birth predicates for is to enforce even like you need, if you go back to the previous slides, right, when we had just the death predicates, what we had was in some sense the birth predicate was implicit. The birth predicate was enforcing value conservation, right? So even if you don't have stable coins or regulations anywhere, your birth predicate in that world would still be enforcing that value is conserved.
That's the simplest.
Yeah, that's the simplest birth predicate you could have, for example, for an asset. Then once you have that, then you can go ahead and generalize that to arbitrary computation, which we did.
It's interesting. And if you present this work other places, it's sort of like an unspoken thing right now that stablecoins, especially those that are running on open networks like Ethereum, may or may not be implementing some sort of whitelist or blacklist at the behest of their regulators. It's generally believed that they're not, but they probably will have to soon.
Yeah.
So if you know more about that, I'd be curious. But if this was just sort of you guys being creative to think about how we could use these, that's another matter than knowing that there's a felt need from regulators that you are addressing.
Yeah, this was not driven by regulatory needs as far as I'm aware.
The operative question from a regulatory standpoint there is if a stablecoin issuer is a money services business, which they always are, who are their customers? The persons to whom they issue and redeem, in which case it could just be a typical ERC20 token. And when it comes to you, you destroy it, and when you create a new one, you create a new one.
Yeah.
Or are your customers every intermediate wallet that hit in the chain of transactions before it comes back to you?
I see.
In which case, how can you possibly
know
have
who they are.
KYC information for those wallets?
Yep.
You can't, and so the only way to use these systems, if regulators were to say those are your customers too, would be to have a whitelist or a blacklist.
Yeah,
But so far as I know, regulators have not forced that issue. At the moment, they're comfortable saying your customers are only those to whom you issue.
Directly interact with. Yeah.
But Facebook's probably ruining that for everyone.
Yes, in that case, you're having this sort of propagating blacklist or something
Whether the
guaranteed.
regulators would trust it, though.
Yes, is another question.
Their knowledge,
Yes.
and regulators might not.
Yeah, be entirely comfortable with novel technology. Yeah. In the future. All right. Okay. So now, once you have these birth predicates, the idea is that you can use it, as I said, to conserve the value, but also enforce some arbitrary policy P, regulation-friendly policy. Okay. And we still have a privacy guarantee. This transaction reveals no information about the birth predicate, death predicate, or anything about the coins, in fact. Beyond that, some coin was consumed and some coin was spent. Okay. And once you have this, you can take this and generalize. There's nothing really specific about coin values anywhere. You could have some arbitrary data payload and arbitrary computation happening here. And this is basically the ZEXE construction in some sense. You can do any arbitrary computation with any sort of data payload in here. Okay. And you don't have coins, you have records of data. Okay. Yeah.
I guess your birth predicate is not kind of network specific, or is it coin specific, or it can be either one? I guess it just
it's in some sense application specific. But for the user-defined assets example, it's specific to the example, but not specific to the token. It's specific to the application, but not to the asset in some sense. And because if you go back here, right, the ID is stored independently of the birth predicate. There's no information about about this asset ID inside the birth predicate. All it says is that, look at all the coins. What are the identifiers inside this transaction? For all those identifiers, make sure the corresponding value is conserved. So this birth predicate doesn't have any IDs hard-coded inside it.
Okay.
Yeah.
Of the predicates, it seems like sometimes you want some things to be public and sometimes private. So you want, in some sense, the birth predicate to be public because you want to be able to prove that value is always conserved. And if you're working with a regulator, you want to be able to prove that you're not avoiding a blacklist or something. But then the most generic death would be something, right, like somebody was able to supply to sign something with a key.
Yeah.
To kill something. So there are aspects of that you need to keep private. So are the predicates public or private, or if they're private by default, how do you prove that there's a birth predicate that?
So your private in this system, everything is private by default, including the predicates. So if you look at a coin or a transaction, you don't know which predicates were involved inside the transaction. What you can do is, if you have a regulator asking you, was this coin, what is the death predicate of that, and you don't want to, or birth predicate, and you don't want to reveal that information, you could have a separate zero-knowledge proof just to them, showing that if I open this commitment, you'll find these predicates inside there, inside the coin. So you could do that's in some sense independent of the system, but it's a thing that you could do if you needed to.
So basically, the transacting parties who are protected by this privacy have the capacity to generate zero-knowledge proofs to third parties about the transaction.
Yes. Yeah. Okay. Yeah. So as I said, you can take that system, and there's nothing specific about assets or coins anywhere in there. You could just talk about arbitrary computation, and you end up with essentially ZEXE, right? Over arbitrary data computation. Okay. All right. So in ZEXE, I guess to summarize, there's a couple of contributions. First, we have to provide a model for computing over these units of data, these records, right, in this UTXO sort of model. Right, and then we show how to formalize or to realize this records nanokernel in a privacy-preserving manner over a decentralized ledger, so no information is revealed about the individual computations. And finally, we implement it and we use techniques from ZK snarks as well as circuit design and recursive composition of snarks. And this code is available online at libzexe.org. Thanks. Any questions? It is also available online. Any more questions? Yeah.
So I apologize for kind of a somewhat non-technical question, but so it seems, so here at Berkeley, there's this economist, Gabriel Zucman, who's written about the hidden wealth nations and people kind of hiding their wealth. I just wonder, it almost seems like if you get a nice privacy coin and it kind of grows in use, it might be kind of easy. So of course you have this nice mechanism there where you might be able to prove that you've paid your income tax or something. But it just seems like that's going to be really tough to implement. So I don't know, I don't know if there's a specific question there. I mean, one question is this just kind of silly to even worry about you know, the possibility of kind of if you're a crypto maximalist and you just imagine, is it silly to imagine a world in which it becomes super easy to hide your wealth and your payments to employees?
We already live in that world, right? We already live in that world in some sense.
I think generally it's actually much easier for the super wealthy. It's actually, and it may even be not illegal for them to hide their wealth. And so I think in this case it might become more accessible to the rest of the world. Maybe that's a sort of equalization. I don't
make it sound nice.
So I don't know if
the future's already here, so it's not evenly distributed.
well, yeah, but I guess I'm not really ambitious for a world in which you know, no one is paying taxes, especially if there's not any other sort of mechanism, for example, for paying for roads, or, you know, my personal preference is to have a social welfare program, for example. And so who's going to pay for that in a world where no one is paying taxes? I know that this is a little bit too much, but I just thought that when I see privacy coins, on the one hand, I think it's great, you know, fancy cryptography and privacy preserving stuff. It's amazing. And then on the other hand, I think, oh man, I wonder if, you know, if this becomes widespread, people who are, you know, it might even be in their best interest. They want to pay their taxes, but it's just some funny bad incentive may prevent them from doing so. So
I think this is like a, you know, I guess classic trade-off right now, right? We have these encryption war, crypto wars as well, right? Where this trade-off between privacy and, you know, law enforcement being able to access the messages of criminals. Like we've had this sort of conversation in another sphere. I think it's coming to this monetary sphere, it's financial sphere. It's an important question, but I think like that's where the sort of ability for you to have privacy while also still proving that, you know, you were law-abiding with the laws at that point in time or whatever is necessary, right? So if you just have privacy without, I guess, any way to show that you know, were following the rules, that's maybe a bad thing. But that's why you want the sort of like selective disclosure property that these sorts of systems grant you, right? Like you have programmability, but still privacy, right? And I guess ZEXE is like one step, hopefully, towards achieving that sort of accountability with privacy. And I guess navigating that trade-off requires a lot more work than, I guess, what we've done here. But that's like a question that I guess is a matter for this workshop in some sense, right? Law and ethics.
As long as you have jurisdiction over employers in your nation, you could pressure them to make payments to their employees in certain ways, and then you can just rely on the typical auditing mechanisms to guarantee that they do. And additionally, you could even perhaps rely on zero-knowledge proofs for the employee and the employer to both be able to prove that, like withholding has been done or something like that.
So I think actually also, I mean, not only do you want to have that you're also going to, I mean, you know, if someone is paying someone who is I mean, how are you going to enforce it? I mean, how are you going to know if someone is not paying by the normal mechanisms? Since you have a privacy-preserving mechanism.
I guess
my question.
I guess it's a little bit harder than right now. Like it'd be cash businesses that pay their employees in cash, and you know these employees seem to be living extravagant lifestyles, and the business seems very successful, but the IRS isn't getting anything from any of these people. What's going on? You know, the zero-knowledge proof that shows that there's some sort of tax compliance is not lining up with what we see in ground truth reality. Or you buy a very expensive house, you know. Maybe this means that we have to rethink, you know, how we do taxation. Maybe it should be focused on things that are very observable, like land.
Okay, all right, very good. It's probably enough. Thank you. I think it's a fun discussion.
It's a fun discussion, yeah.
So thank you.
But this is very interesting that there could be some level